we have a couple of different ways to define factorials. And we use the exclamation mark. Does anyone know why it's an exclamation mark? Because excitement, you know? You read it as n factorial. Now, I'll tell you why. There are different kinds of functions, right? That's going to take a seat. Different kinds of functions, right? And they all grow at different rates, okay? So for instance, a function like this, okay? As x gets larger and larger and larger, y also gets larger and larger and larger, right? But how does it do it? In what way does it do it? It slows down, doesn't it? Okay, it never actually stops, no turning point or anything like that, but it slows down, okay? If you had to put it in rank order, what do you think would be the next in line? What would be a faster graph than this, but, as in it grows faster, but not like I want the immediate next one. What do you think would be a good thing to call it? Any takers? I reckon, like this is curved, right? I said, you know, it's growing, but it's slowing down. If it didn't slow down, what would it look like? Something like this, right? That's not slowing down. We call this, it has a name. This is logarithmic. This also starts with an L. It's linear, right? And it's x or 2x, or it's the same kind of idea, right? Okay, it's constant growth. What do you think would come next? Now, I think we are going to get to exponentials, but before then, there's one we're missing. There's what we call polynomial growth. Okay, now you're like, couldn't we put x squared, cubed, 4, 5, 6, and so on all the way there? I suppose you could, but really, they're all the same kind of growth. They all exhibit much the same kind of behavior, right? And when you do the derivatives, you can see it's borne out by that. Right? Exponentials come in next. Now, exponentials are fast. They're insanely fast. It's hard to illustrate how fast they are, okay? And that's why exponential growth, in wherever we encounter it, it's crazy. We use it as a language to say something's growing really fast. Oh, it's growing exponentially, right? There's something faster than exponentials. It's the factorial function. Next to the factorial function, the exponential function looks like a snail, right? There's no way to put them next to each other, right? So they put an exclamation mark. That's what they mean, okay? Now, if you had to give a definition of the factorial function, it equals, what does it equal? What's on the other side of the equal sign? Well, you're going to say, you start with n, and then you multiply by something, don't you? You multiply by the previous number. And then you multiply by the number before that, and you keep on multiplying until you're going to get down to 1, and then you stop, okay? Now, there's a variety of reasons why this is an all right definition to start with, but not good enough, okay? For starters, when you think about, okay, what might a number be? I could put it in the example, 5 factorial, and it fits the definition just fine, okay? But then some numbers quite clearly make it break, right? Like if the number isn't a whole number, what's that? Right? If the number is 0, which is kind of an important number, what's that? We've discussed this before, actually. So there's a lot of reasons why this is an okay definition, but we want a better one. Okay. So a better one would be, where did I rub out my thing? Hiding. Male television, sorry. A better definition than this would be a recursive definition. Now, recursion, some of you are familiar with this idea. A recursive definition defines something in terms of itself. And you think that's a bad thing, isn't it? Well, not if you do it right. I'll show you what I mean. Okay? I can say n factorial. Well, what is that? Okay? Let's just look at the beginning here. Okay, just look at the beginning. We know it has to start with whatever that number is. Okay? Now, what do you multiply after that? Well, I'm going to write it recursively. I'm going to write it in terms of factorials. N factorial is n times some other number. What is the other number? And the answer is, it's n minus 1 factorial. Okay, that's what it is. Okay, so this recursive definition is much more helpful to us, right? And then you get down to, just like in normal recursion, you have to go down and down and down. You climb down the ladder, and eventually you get to the bottom, which is 0 factorial equals 1. Okay, so this is a better definition. Okay. Not only does it, deal with all these guys in between, okay, but it helps you work with things. Okay. Example. 5 factorial on 3 factorial. Now, I've chosen small numbers so it doesn't freak your brain out. Okay. I know you can do this without any sophisticated techniques. Okay. But my point is that you can use this recursive definition to work with it a lot more easily. Okay. In order to cancel this out, all I want is a common factor. That's how we cancel things out, right? Now I can find a common factor by using this definition, right? Okay, 5 factorial. By the definition, what's it equal to? It's n times n minus 1 factorial. Cool, right? Now that's good, but we're still not there, right? We have to go again. We have to go down the ladder one more step. So I'm going to do that. 4 factorial by definition is 4 by 3 factorial. And now I have the factor I was after. And of course you get your answer of 20. Okay. Now this was easy because 5 and 3 are small numbers. Okay. But when you have n's and r's and other things, you don't actually know what they are, right? This technique, right? Some people call it, the textbook likes to call it unrolling a factorial. I guess it's kind of like, this is kind of like a thing all knotted up on itself, right? And this is having it unrolled just a little bit, right? And now it's like, oh look, see that part? That's the end. I can see that and I can deal with it separately, right? This here, it's rolled up enough so that the rolled up bits are the same, the 3 factorials. Okay, and you're like, look, what's left over is the 5 and the 4. That's how much I had to take out. And then I've got my common factor. Okay? So this seems simple, right?